Ja, welcome to today's lecture of ESP, Einführung in die strukturierte Programmierung, or Introduction to Structured Programming. Yeah, it's great to see so many of you here in the lecture hall today. We're happy to be back here. And yeah, today we have a great topic, really cool topic, to be honest. It's about memory and memory management. It's a very important topic, not only for this course, but also for further courses, especially in the fourth semester, or depends on the study program. But many of you will need the content of this lecture today, also in other courses.
So it is like an introduction to memory. We will not cover all of the memory stuff here because it is a very, very large topic, and there are, I think, 2 like dedicated lectures, or even 3, I think, with computer organization. So there's a lot about memory, and this should be a brief introduction into memory and how we will use it in C. Okay, but before, as always, a bit of organizational stuff. It's very quick. Today we are in week 6 already, so today is also the handout of the weekly exercises of the 6 times, and it's the only weekly exercises for the 3rd assignment. That's why I think we have 5.
Exactly, we have 5 weekly exercises, all dedicated to assignment 3. So all with the topic around memory management, dynamic memory management. And yeah, it's the only weekly exercises that are related to assignment 3.
Yeah.
So
assignment 3 is only about memory management. And the deadline for the weekly exercises is then the 11th of December. So about a month for you to submit it. All right, then let's do a short recap about pointers, arrays, and whatever we've done last time. And Michi and Julia also talked in the practicals. So this is the first, let's say, code snippet with a problem, and you should guess, or not only guess, but find out what's the output.
Yeah, as always, just scan the QR code that is shown here, or visit the website and enter the code. I don't know why it's white today. It's a bit of a surprise, but yeah, doesn't matter. So what do we have here? We have an integer array and with a pointer, the address of the element at position 1, so the 2nd element. And then we have a printf. We increase the pointer, so we've just seen it in the practicals, the pre-increment, and then we dereference this pointer. So what is the output? Is it a value that is inside of the array we have declared and initialized, or is it maybe an address that is printed?
It's not that easy to spot that it's a value or an address, because there is an indicator for it.
Yep.
This %d means it's a digit. It's not a pointer or an address.
So let's wait a few more seconds and then we will see.
Okay, I think we can continue.
Yep.
What's the result? Yeah, it's 10.
Great.
Why it's 10?
So let's see what happens in the this line here. So
it doesn't. Yeah. Unfortunately, the laser does not work if it's Slido.
Okay. We can see in this line. So we store the address of the 2nd element. So the address where the element 5 is stored in this pointer here. And then in the printf, as we've just seen in the practicals, we first increment the pointer. So we say, go to the next element, element 10, and then we dereference it, and that's why 10 is printed. So we go to the next element by using pointer arithmetic, and then dereference the pointer, and then is printed.
Another example is regarding command line arguments. We also talked briefly about command line arguments. And the question here now is, how should we execute the program that it's printing 21 in the end?
So in this code snippet, we are expecting two arguments, or we are just considering the first two arguments actually. And yeah, then we just build the sum of these two numbers. So we are looking at a program execution, or a command for a program execution that results in printing 21. So maybe we can just go through the answers here. So here we have three arguments. So the first one is always the name of the program itself. Then we have two additional arguments, it's 10 and 11. Here it's a bit tricky, I would say.
Yeah, 20 plus 1.
So is this one argument? Is it, or one additional argument? Is it two additional arguments? It's actually just one additional argument because, yeah, it's a string you pass as a command line argument. So this is just one argument. Here, this is also just one additional argument. And here we have three additional arguments.
Okay, so
let's see
how you voted. Okay, so the first one, very good, 77%. It's 10 and 11 as additional argument to the program, which means it parses these two, then converts it to an integer with the artoy function. The second one here is also correct.
It's also correct.
It has more parameters, but the last parameter is just neglected. What would happen if I call a program with these two below here?
So we would access an index of the array that is not passed to the program. So we have just two parameters or two arguments. And in this line, we would access the third argument. So an element at the index position 2, but we don't pass three elements. We just pass two elements. So
it does not exist.
Doesn't exist.
I think it will be a segmentation fault then.
Most likely, yes.
Yeah.
Okay, but great. Many of you got it correct.
Is there a question? Yes. You mean here? So argv0 is always the program itself. So argv0 means this /program.
It's literally the string /program that is stored in the first element of the array.
But yeah, good question, because it's a common pitfall to take this one, then convert it to an integer, and then the program stops because you want a string converted to an integer. All right, so we are talking about memory today, and memory needs, again, a very important topic, which is pointer, but I think it's the last time for now where we talk explicitly about pointer. From now on, we just use them.
We apply them, we use them.
Yeah, but as a short overview, once again, we have addresses somewhere in the memory, and we will have a look at memory like this today. And we want to know the address of a variable. We can use this address of operator. We already saw that many times now.
Yeah.
We can use this %p to print a pointer.
As a format specifier,
Yeah.
Exactly.
And we can have a pointer. So we have a pointer variable where I can store the address of a variable, printing out the address in this case. And dereferencing again means I use this pointers, I use this asterisk here in front of the variable, and then I can go from the actual pointer to the address and print the value there. So far, so good. I think that, we showed that many times now.
Yeah. Also important concept, we have seen it in the practicals today, the difference between call by value and call by reference. Just a very brief recap. So here in this example, we pass the values 5 and 6. So literally the values, not the addresses of the variables, to this function here. And if we modify the values or the the values of the variables here in this function, they are not anyhow modified in this function, in the main function below. So this is called by value. We only pass the values. If they get modified, it has no effect on the, in this case, on the values or variables in the main function. On the other hand, we have call by reference. Here we actually pass not the values, but the addresses of the variables to the swap function. And if we now, thank you so much. If we now use the pointers that are passed to the swap function, we can modify them using the asterisk, so the dereference operator. And now if they get modified in the swap function, they also have other values in the main function if we use them again. And we've also talked about arrays as function parameters. So in this case here, we pass the array numbers to this function here to find highest numbers. And we can just use the array in the function, but actually it is just passed as a pointer. So we pass not the values themselves, but the address of the first array element. And but we can use it as an array in the function that we have called. And we've also talked a lot about pointer arithmetic. So we've heard it a lot today in the practicals. We can use the index operator, so the brackets here, but we can also use the pointer arithmetic by adding some values and then dereferencing it to get the same results as we would use with the index operator. So are there any questions to pointer arithmetic? Yeah. Especially, do you have any concrete answer?
Go ahead.
Especially in advanced settings, you might use pointer arithmetic, or there might be some use cases.
But it is up to you in general. So if both works for you, you can choose whatever you want.
Yeah. Sometimes it's more convenient to use pointer arithmetic, sometimes to use the index operator. So it's really up to you. Are there any other questions?
I think we covered that a lot in the, I don't know, last 2 hours. So we also talked about the size of objects or of data types, and the size of a character is 1, the size of an integer is 4. But what we saw is, regardless of which type of pointer you have, if it's an integer pointer, character pointer, or any student pointer which you created in a struct before, it's always 8-byte. So a pointer is always 8-byte. Even when it's a pointer, it's again only 8-byte.
As soon as you have a pointer variable, so with a data type pointer, it's always 8-byte, independent of the actual data type that is here in front of the asterisk.
Yes, so this again is a short quiz. It's not on Slido, but just think about it. What do you think is the output of that one?
So we've seen a similar code snippet just before in the practicals. So we have a string here, hi, and we want to modify one value or one character in the string. So what do you think is the output if we print now the pointer and if we print the array? Do you have any idea, any suggestions? So who of you think it will print hi twice? Just raise your hands. Okay, no one? So who of you thinks it will print hi and si, si? Okay, again, no one. S-I-C, si, whatever. And hi? C, S-I and C? Yeah, there are some
Interesting.
Hence
So
rest.
everybody else has no opinion, or is there another thing we are forgetting?
Yeah.
No, so the output is just SI and SI in both
Yeah.
cases. So it's basically the same string we are
Yeah.
operating on. So when we have a memory like this, we have the text and it's stored consecutively in the memory. And then we have a pointer, which is somewhere there located, and it points to the exactly same memory location, which means that we modify the same string in this case.
So there's only one string, but there are actually two variables that are pointing to the first element of the character array.
Okay, I think we made our point clear now.
Yeah.
With strings, arrays, pointers, whatever. Let's come to another short topic before we can go to memory.
Yep.
And it's type conversion. And I think you already saw it a few times also in the lecture, in the practicals.
Yeah.
I think also today. And Michi always said, don't care about that. It's not important. So we want to convert types from one data type to another. You already saw it also when we explicitly convert, for example, a string to an integer. So we had this atoy or atof function, which takes a string and converts it then to an integer or to a float. But can we also, for example, convert an integer to a float or the other way around? Is that possible? And yes, it is. For example, we have when we have an integer, we store 4 inside, and then we just assign it to a float. The output is 4. So this works. This is a so-called implicit cast. So the compiler does this type conversion for us. We can also do it explicitly. So we write it here in front of the variable, cast this integer to a float. It is exactly the same program behavior, but the second option here means we know what we are doing and we want to convert this integer to a float. In this case, it works because 4 is then stored as a float and everything works fine in this case. But let's see another example. We have an integer with a value 257. We explicitly cast it to a char. What do you think is the output?
These are some kind of questions that
Yes. Yeah, that's a good idea, but it's not correct, to be honest. Yes? Yeah, it's going to overflow and the output is 1 because a char is only from 0 to 255.
Yeah.
So it starts again with 0, which means it outputs just 1. So this is a pitfall if you cast on your own, which you might occur. At the exam, for example. Yeah. Another problem, let's say we define pi. I know it's not very well defined, but we do it even worse and convert it to an integer. What's the output here? I think you were first, yes. 3.
It's 3, yeah.
The output is just 3. Very roughly approximation of pi, yeah. But all the decimal places were just removed, and the integer can not hold the decimal places, so in the end it's just 3. So be careful when you do these type conversions. Sometimes it makes sense, sometimes it can be very, very tricky.
So if you use this typecasts, really think about if you really need this, if you want to have this behavior, or if it could lead to some not desired behavior.
Next one. Again, we want to cast a string which has 1, 2, 3 inside, and we want to convert it to an integer. Maybe this would also be the first thing we wanted to do if we want to convert it. It works in Python and many other languages, but unfortunately, the output is something like this, because what we do is we cast the address of the string to an integer, and it's a very, very large number. I don't know what it is. So the output is here not what we wanted to have. That's why we used the atoy or the strutor functions before, because they are doing this correct type conversion for us. Yes, we can also cast pointers and convert pointers in another data type, and that's what we will use today. Let's say we have here in the main a number, an integer, and a float, and we just have a function that sets the value to 0, but I don't want to write a function or two functions, one for the integer, one for the float.
Or even character.
Or for all the data types, So what I can do here is I say I convert it to a so-called void pointer, and void in this case, we will see it later, void in this case means not nothing, but it means arbitrary. So beliebig in German. It can be basically everything.
Yeah.
So we cast it to a void pointer. We cast the address of the number and of this floaty variable to a void pointer. We take the void pointer, and in this case here, we cast it back to a float and set it to 0. Yeah. So, any questions to this? We will come to that, I think, once again in a few slides. Yes, also with the pointers.
Yeah. So are there any questions to type conversion, typecasts?
It looks very straightforward, but it has some pitfalls in. Yes? So, you mean if I only cast the first one? If you okay. If you dereference it, it's still a string or it's a character, and you will get then the ASCII word, so the ASCII value out of it. Yeah, this would kind of work, but you have to calculate then back the number. Yeah. So it's not the real number because, for example, in this case, one is, I don't know, ASCII 82, I don't know, something like that. So you will get the value 82 instead of 1.
So for that you can use the string 1 and then use atoy or strutor and then get the number.
Any other questions? I think that's the pretty easy part for today. So let's continue to some more additional data types before, or what we need before we can go to memory.
But a very important data type.
Size T, we saw it already a few times.
Yeah, and you will also see it when doing the assignments, working the assignments, and also when using malloc, realloc, calloc. So size T is actually just a type for unsigned long. What does it mean, unsigned? So it cannot have any negative values, so it can only be 0 or any positive value. This has the great advantage that we can use it, for example, in loops. We'll see it on the next slide. And yeah, it's a special data type to just store the size of the variables or to pass the size of variables because it cannot become a negative value since it is unsigned. So yeah, very important. If we would want to print a size T variable or the value of a size T variable, we should not use %t, otherwise you will get a compiler warning. You should use %lu as a format specifier. Yeah, it's long.
It basically means long unsigned. Yeah.
So
yes.
But
yes.
Yeah. We just store the value of size of int in the
size of the int. It's complicated. Yeah. The size of an int is 4. Yeah. So basically, what we store is the value 4, and we store this value in a size t in an unsigned long?
But that's a great question, actually.
Yeah.
Yeah. So
what is size t again?
Yeah. Just a quick explanation. It's the maximum size of the possible object that it could have. So it cannot become any larger, but it cannot become negative. So it's great for iterating through arrays. So if you use for loops, for example, since it cannot become negative, you cannot have any out-of-bound accesses here. But yeah.
But basically, I would say for the exercises, for everything we are doing here, an integer would be sufficient. But
in most cases, yes.
You can definitely also use size t. You will see it in other lectures like operating system. Yeah. Everything is stored in size t. That's why we just show it to you. It's basically just another type deft data type of an unsigned long.
Okay, we also have the void pointer. We've seen it just before when we showed the function that takes a void pointer as in this function here. So we have now two different voids here. So we have the return type void, and we have the data type for this argument pointer, which is also a void pointer in this case. So now we have exactly these two different meanings of void pointer. In the first case, so for the return type, void means nothing, so we don't return anything in this function. And in the second case, we have the void pointer, which means we can pass actually anything. So this can be an arbitrary data type. We can pass a void pointer, we can pass a character pointer, integer, double pointer, whatever. And these are the two different meanings of void pointers, or the keyword void. And in this example here, we then just have a switch case with the different types that it could have, and then we just use a typecast here. We say, okay, if the type is I, then we typecast it to an integer pointer and dereference it. If the type is F, we use the typecast for a float pointer, and the same for a character pointer. So we can pass a void pointer, but it can have actually different values, so depending on the different data types.
So this example is very artificial. So I would not write a function like this, but we have to find a way to show you how void pointer work without having memory, but we will see in a few slides where we actually use void pointers very, very often when we talk about dynamic memory.
And why they are necessary.
Yeah, so we will see it quite a lot, and maybe more practical examples like, and not like that.
Okay.
All right, now I think we have everything that we can start with our memory management. And I admit memory management is, besides pointer, one of the hardest topics to learn. So this is maybe the most important lecture. I think we say it every time, but today it's true.
Yeah, does it really?
But again, we want to make it easy for you to understand. So let's talk about memory and what do we actually mean when we talk about memory. I hope, or I think most of you know something like this. What is it? I hope you have seen that all. It's a RAM. Yeah. Or we use sometimes the name main memory, in German Hauptspeicher, but you know it maybe also as RAM. But I think we will now use the term main memory, but it's basically the same. So we see here a lot of, it's in this case, 4 places where we can store values. So you can think of like a grid we see here, and in each of these 4 memory stores, we can store some values. For example, it looks like this. We have here a few bits, and in this case, so this is 1 bit, and in this case, this memory can store 48 1-byte values. kind of very, very small main memory.
Yeah.
Usually an 8 gigabyte memory can store about, help me, 10 billion? Is that billion?
I think it's billion, yeah.
10 billion values. Yeah, so 10 billion 1 byte values. 8 gigabyte is already quite low nowadays.
Yeah.
So
It's
yeah.
true.
So just to give you an idea how the main memory is structured and look like. So this memory layout, and this is again just a draft, and it's not really like that, but it's a good mental model to think of what the memory looks like. So we have very, very low addresses here, and we have very, very high addresses. High addresses, FFF, just means very, very high. And the upper half of the main memory belongs to the operating system, so you cannot touch it. It completely belongs to the operating system. I will not go into detail too much here. This is then the lecture operating systems, but we are only working in the so-called user space. User space is the memory region where we as a programmer can execute programs. And when we look at this user space, it's again structured in different regions. So let's have a closer look into that. So now we have only the half of it below, and we have the code segment. The code segment is where your code of your program is stored. So yeah, also your program is stored somewhere in your main memory because it should be executed, and you need to store it somewhere. Then there is the data segment where you can store constants or global variables. The evil global variables are stored there, but also constants are stored there, and we will see it afterwards. Then maybe you have heard about that because we used that term already a few times, the stack, and the stack stores all the local variables. So in every function has an own stack, and it's always inside of this memory region here. And then we have another one, which is kind of a mysterium, the so-called heap, where we have a so-called dynamic memory. And this is the memory location we did not use until now, but we will use today.
Exactly. And just to translate, heap in German means something like Haufen.
Yeah, it's very uncommon to say it in German, but it is kind of a good explanation because it's not stored like structured on a stack where they are in a continuous region. It's basically just, I don't know, a collection of different locations and not stored continuously. Okay, so kind of motivation why we would use dynamic memory again. We have a function with a create array. We have a create array function which creates a local array on the stack and initialize it with 0 and then returns it. We know you should not do that.
No, that's not good.
That's not good. But what happens here is when I execute the program, then this new stack of this create array function is created where I have now my array inside and my I variable inside. And when I return, so I have this array here, when I return here, this is gone, so this memory location is not accessible anymore, so I cannot use the array here because it's already gone. This is a problem.
Yep.
And this is because the stack works like that. So this is what we saw about lifetime and scope.
Yep.
So the lifetime of the array is as long as the function is available and is running.
So just to clarify it again here, so we have one stack, but inside of the stack we have different areas. So let's call it stack frames. So we have the stack frame of the main function here. And we have an additional stack frame of the function create array, and we would have other stack frames if we would have additional functions. But once, as you said, the function is not available anymore, it is executed, the stack frame is gone. You cannot access it anymore.
Yeah, so returning local arrays is never a good idea. Really never? We have a solution.
Yeah.
So, okay, we have a solution now, and it's called dynamic memory. So what we can do is we can write something like this very awkward looking line of code. Mm-hmm. And now this would work. I will go into detail what that means in next slide, I think. But this here just means we are allocating memory on the heap, so dynamic memory, and then we can return it. Why can we return it? Because it now ends, it does not end at the end of the function. So I can use it here again because the lifetime is different to a stack variable. I can create it here and then use it as long as I want. It's not deleted as soon as the function is over.
So if we would have the variable here that is stored on the stack, so a stack variable here, the lifetime would end with this line. But now we return the array, and the array still exists because it is stored on the heap. So that's the difference between the lifetime for variables on the stack and on the heap.
Yeah. So what is dynamic memory now? Dynamic memory is exactly this data region. It's the heap. So data that is stored on the heap, and the cool thing is storing data on the heap is, in the beginning a bit hard to understand what this line of code means, but it offers so many cool possibilities now because we are not bound to a function anymore. So what this actually means is I have a stack here with my main function. I have the create array function on the stack, which has, again, the length. This is just this variable here. And we just have a pointer to the heap. So the array is not stored here on the stack anymore. It is stored in another region on the heap. And I just have a pointer to this memory address.
Yeah, so we have a pointer variable that is stored in the heap, but this pointer variable points to some region in the heap.
Yeah. So what the cool thing is, when this create array here is over, so this function is over and I'm back in the main, this array here still exists. But I have to, of course, I have to take care that I do not lose the pointer to the array. So when I lose this pointer here, I will also lose the array because I don't know where it's stored. I have this pointer and I have to return this pointer maybe from this create array function, and then it would work. But what's the differences now? Memory on the heap is allocated during runtime instead of the stack where we have it, or it's calculated at compile time. The heap memory is really allocated during the runtime. There is one bad thing we have to take care of. We saw before that it's not deleted when a function is over, but we have to take care about it. So we have to explicitly delete this memory or delete this array in this case, and free it once again.
But we didn't have to do that for variables that were stored on the stack. But now, when we use the heap, we have to take care about the memory. Yeah.
But the data is not limited to the lifetime of functions, so that's a huge advantage. Okay, how can we do that? There is a function called malloc, which basically stands for memory allocation, and it takes one parameter. It's called size. It's of type size t. And basically what you can do is, a number, you can hand over a number, the number of bytes you want to allocate. Can be 1, can be 1,000, can be, I don't know, 1,000,000.
Yep.
Depending on how much memory you want to have. So most of the time, you know, I need an array of, let's say, 100 byte because I want to store 100 characters inside. Then I call malloc, and what malloc returns is a void pointer to the location on the heap. In this case, again, void means not nothing, it means arbitrary. So it's up to you how you use this memory. You can use it, for example, for characters, then you can cast it to a character pointer, or you can use it for integers, then you can cast it to an integer pointer.
So yeah, that's again the great advantage of void pointers. So we only have one function, it's called malloc, but you can allocate memory for different types of data. You can allocate it for characters, for integers, whatever.
The problem is this memory is again not initialized, so we don't know what's in there. You need to include another library for that, the standard lib library. So there is the implementation of all these functions. And on error, so if an error occurs, malloc returns null. We already know this null.
The null pointer?
Yeah, it's a null pointer. Any ideas when malloc can return null? So when can be an error? Yes. Yes. Yeah, when there is no more memory available, because you have limited amount of memory on your computer. So when there is no more memory available, then you might have a big problem because there is no more memory available. So most of the time, you just want to close or exit your program, return it and exit this, because it's not a good idea to continue then, because you have like another huge problem on your computer in this case. So yeah, we already stated you can use the return value and make an implicit or an explicit cast to an integer pointer and then store it in an integer, but you don't have to write this because it's casted also implicitly. So if you omit this, it also works without warnings, without errors.
Could be just for you as a programmer to explicitly write the typecast, but you don't need to write it.
Very, very important. Always check if malloc returns null. So what you always should do is, as soon as this line is written here, you are getting some memory, in this case the length, so whatever the length is in this case, depending on the parameter of the function call, times size of int. Size of int is 4. And let's say I want to create an array of 4 integers, so I call this function with 5. So I create here a memory location of 5 times 4, which is 20. If it works, this if is wrong. So I can come here and initialize it and then return it, and this works perfectly fine. If it does not work, I should return here because I cannot access the memory because this pointer here is null. And if I want to access it, it's basically like you are accessing the memory location null. And the operating system knows that you are definitely wrong here. It's not your memory address, and your program will crash immediately.
But it's very important to have this null check. So malloc returns the pointer to the memory that is usable on the heap. And as David said, if you wanted to access the memory at the address null, that's definitely not good, and your program will crash. immediately.
The good thing is you will see it immediately because the program crashes. Yeah.
But that's not what we want to have most of the time.
Yeah.
So
We can also improve this code again because what we get returned from malloc is a pointer to a memory location on the heap with the size what we demanded here, and then we iterate through and set everything to 0 because we don't know what's there. And there is another very, very similar function which does that for us. So calloc is pretty much similar to malloc, but the only difference is that it returns again a pointer to the address and writes everywhere 0 inside. So the memory is set to 0. In this case, we don't have to use something like this. If we use calloc, we know that the memory is always 0. And in most of the cases, or let's say in many cases, you want to have an array or a memory location where you know it's 0. Sometimes you don't need it, but in many cases, you want to know that there is a specific value in this case.
Yeah, and
0.
one more difference between malloc and calloc.
Yeah.
You have here 2 parameters that are passed. So the first one is the number of elements you want to allocate, and the second parameter is the size of these elements. So if you would want to allocate memory for, let's say, 100 integer values, you would first pass 100 as the number of elements, and then size of int for the size of the data type.
So how many bytes did I get then?
What did I say, 100?
100, yeah?
Times 4 should be 400.
Should be 400, exactly, yeah. So yeah, calloc has the advantage that it always initializes the memory with 0. What does it mean when we talk about memory management? So what is this management again? We already talked about it a bit. The advantage is that the array is still available when the function ends. The disadvantage is the array is available after the function ends. So you have to take care of it and delete it as soon as you don't need it anymore, because otherwise you have a problem.
And you also shouldn't lose the pointer.
That's another thing, yeah. But you have to do the cleaning. Cleaning up means you have to free the memory. If you don't do it, so let's say again we have our create array, we allocate memory on the heap, in this case with calloc, we return the array, everything works fine, but then we return our program from the main function and we call valgrind. I think it's the first time we talk about it, but I think in the practicals they already showed it. And when it comes to memory management, this tool is very, very useful.
It's great.
You will, if you haven't used it until now, you will use it from now on when you're working with the heap, because it says when you execute your program and hand over the command valgrind in the beginning, it says that when the program exits, you have 20 bytes still available and you definitely lose it. So they are lost, and these are exactly these 20 bytes that are allocated here. How can we fix that?
Maybe there's a function?
There is another function called free, and this free function takes again just the pointer to the array, a pointer to the location on the heap, and when we just free it, free just means, okay, I don't need that memory anymore on the heap. Please free it, and as soon as I execute it, it's also gone there. It's not really gone, it's still there, but it's not again reserved for us. So maybe another program or another function gets this memory location again and writes something different. Interesting question. Can we still access this area after that?
So we still have the pointer, right?
We have the pointer, so this is available here. We have a pointer to somewhere on the memory location, somewhere on the heap.
Yep.
What happens then? So if I have a pointer here, I just print the pointer. This works very, very well. But then I free it and I print it once again. It points to a memory location which does not belong once again to us. And I will again have a problem when I execute it with Valgrind, because it says again, you have an invalid write of size 4 at this memory location here, because it was already freed. So you already freed it and then you accessed it, and it's in this line. It's a so-called dangling pointer. That's a pointer that does not point to a valid object, but you still have the pointer to it. Any questions to this? Because this is like the basics, but very, very hard sometimes to understand. Any questions to memory management in general? Yes? Not a function pointer. The function pointer is something different. But you just need a pointer to the memory location.
And if you have functions, you should pass the pointer to the functions or return it.
So basically what you get back from calloc in this case, it's just a pointer. So it's again just an address, as we have seen always, but now we are not storing another address somewhere on the stack. We are storing an address of a different memory location somewhere on the heap. But it's still just an address, and it points to the beginning of an array that is now stored on the heap. So, like this. It's a pointer to the beginning of an array. It's pretty much the same when we have an array on the stack. This array then is continuously, so 0, 1, 2, 3, 4, and so on. They are in the memory next to each other or after each other. And the pointer is just, a pointer to the beginning of the array.
Does this answer your question? You mean the return type? So the return type of
this one here. Okay, yeah.
Let's assume what would happen if we don't return the integer pointer array. So, and we don't store it in the main function. If we just allocate the memory on the heap here, what would happen? Does anyone have an idea? Yes? Yeah. Yeah, we would lose the pointer. We wouldn't know anymore where on the heap, so where on the memory, the array is stored. So
because we lose not really this, but we lose, oh, sorry, that was wrong. We lose, so we have here our create array stack, and we have here our, that's hard, array pointer, which then is deleted. Now it's deleted. And we lose it, so we cannot have access again to this memory location there.
So the memory still exists. It's still reserved for us, but we cannot access it anymore because we don't know where it's located.
And the function here, this create array function, returns an integer pointer. So it returns an address. It returns the address of the heap where this array is stored.
That's why in this case we need the return type integer pointer. So, does it answer your question? Perfect. Great.
There was another question. Yes. Why would I use it? That's a great question. There are many different scenarios where you have to use dynamic memory. Think of your user can have an arbitrary long input. So you don't know how long the input is. And on runtime, so when your program runs, currently without dynamic memory, you can only have like, I need an array with 1,000 characters, 1,000,000 characters, whatever. But you have to define a specific number. But with dynamic memory, you can always create a new array with, and we will see it in a few slides, to make it even bigger and bigger depending on how long the user input is, for example. Okay. What's the advantage from malloc instead of calloc?
One advantage of realloc is definitely that is initialized by default to 0. So that's one great advantage.
But malloc, why should I use malloc?
Yeah.
The only advantage of malloc is it's a bit faster because it doesn't have to zero all the memory. So if you know that's not important that the memory is set to 0, then you should use malloc. But in our course, it's perfectly fine if you always use calloc. We are not bound to this very, very specific and test cases. You have enough time for all the test cases. So we don't have this restriction that it's your program should end in a specific time. Mm. Any other questions? Yes, I think there was one question also there.
But here, in the meantime, another question.
Oh, yeah.
Yep.
Yeah. Exactly the same. So the question is, how would we allocate a two-dimensional array? You have seen today in the practicals how a two-dimensional array in the stack works. It's not really two-dimensional, it's one-dimensional. And the same, it's here, it's just one-dimensional on the heap.
So let's assume you would have a 3 times 3 two-dimensional array. It's just 3 times 3, it's 9 elements. So you allocate memory for 9 elements in this case. Okay, is there another question? Yeah?
So the question is there any benefit of initializing the array on the heap? So if you as a programmer know that's not important to you, there is no advantage. But sometimes, let's say you want to count something and you always start counting with 0. So you explicitly want that all the memory is 0 because you want to count something, then it's the benefit of you don't have to initialize it and set it on your own because it's automatically initialized.
Yeah, it depends a bit on the use case.
Yeah, it depends on the use case, yeah.
If it is required to have 0 for every element, or it doesn't matter. So.
Yeah. If, for example, if you have a for loop somewhere here after creating the array, which then writes something directly in the array, it's better to use malloc because it's not needed to set it to 0 when you write it again another value inside.
Okay.
Good question. Is it bad to use the heap instead of the stack? It's a definition of bad and good, as always, I would say. But let's say that a lot of things you're, for example, using in Python or somewhere else are stored on the heap. So the heap is not slower. The heap is has no real disadvantage, I would say. Sometimes the stack has, because the stack is bound to a specific limit. It's about 8 megabytes. The heap can be very, very large. So the heap is in most of the cases maybe the better option, but in this course again, there are no differences. Not really. There's no real problem always using the heap, but depending on the use case again, you have to allocate the memory and you have to free it and take care of the pointers. So there's a bit of an overhead for you to keep in mind. And when you know you have a variable which you only use in this function, then I would prefer always a stack variable because you don't need it somewhere else. Yeah, and it's easier just to declare it and it's deleted automatically. But very, very good question, because sometimes I see students for every variable they are allocating one byte, for example, for a character and then free it 3 lines afterwards, so it's not necessary to always use the heap. Okay, so we still have a few more minutes left. I think we have to hurry a bit.
Yeah.
But the question before was, why should I use it? And my answer was when we need an arbitrary amount of memory.
And if the program flow requires it to have different size of memory. And in this case, we have just a size of 100. But what if, as the program flow requires it to have even more input? If the user can enter some values or more values multiple times, or to have an arbitrarily long user input. And for this, we can then use realloc. So it's the third important function we learned today. Realloc can be used to change the size of the memory, so it can increase or decrease the size of the memory. And again, it has 2 parameters here. So the first one is the original pointer you got from, let's say, malloc or calloc. And the second parameter, again, is the size you want to reallocate on the memory. It can be greater than the original size, it can be less than the original size. But what is important, the content is completely unchanged. It remains the same, but it's not 100% sure that the pointer that you got from malloc or calloc will be the same when you call realloc, and that is returned by realloc. So the memory can be in some different area of the heap. It's not guaranteed to be in the same area.
Yeah. So basically the first argument is an existing pointer to the heap, previously allocated with malloc or calloc, and it returns again another pointer to the new memory location, which is maybe larger, or it can also be smaller than before.
And again, it's very important to perform a null check, and it's also a good practice to use a temporary pointer, because if you pass the existing pointer, the original pointer, and use this pointer to store the return value of realloc, then the access to, or the variable with the address that is pointing to the heap, it's gone because it's null.
So basically the third assignment is just about that, as a short hint, So we will release it only, I think, in 2 weeks. I think in 2 weeks.
2 weeks.
So you are working with malloc, realloc, calloc, and let's say a short environment, not a huge program, but you have to use all of them to get a feeling how to use realloc, malloc, and so on. Yes?
So the question, if I got it right, if we have some specific area in the heap and we call realloc and want to increase the, so And if there is already another reserved space for any other variable or whatever, and if the content or if the space then overrides the existing content from another variable, for example. If this is the case, then the area will be moved to somewhere else in the heap. And then that's also the case where you will get a pointer that is different from the original, from the existing pointer.
So realloc always assures you that it finds a memory location somewhere on the heap that is big enough. All right. How can we use then this memory? Of course, we can use it like a usual array, but sometimes we want to copy something inside, which is a bit larger, not only setting one or two characters there, for example. And there are functions like memset or memcpy, which is basically memory set, where you can set
some specific value.
Yeah.
How many times? Yeah, n times.
To an array, exactly. And memcpy is where you have a destination, a source, and it basically copies n address elements from the source to the destination. So if you want to copy a string, for example, strcpy is another example of it. Memcpy is just more general if you want to copy, for example, integers. You already have an array of 10 integers. You have now another array on the heap. You say memcpy everything from the source to this, and it goes through the array n times and copies all n elements to the other array. It's not really bound to heap. You can also use both of them if the array is just on the stack, but it's very common to use it also on the heap. How much memory can we allocate? That's very funny, and I think we want to do it because let's say our machine is quite big with 32 gigabyte RAM, and we have something like this. We have a malloc call with a very, very large number. So this is a bit shift. And
in this case, it's 1 gigabyte because we shift 30 times to the left. And it's 1 gigabyte, and we do this 36 times in this case.
So when we have 32 gigabyte RAM, we would assume that it should stop when 32 gigabyte are allocated. But it's not. It goes further and further. We are here at 36. And it goes even further to, I don't know, very, very large numbers.
That'd be great to have.
How does this work? Do we have more than 32 gigabyte RAM?
Maybe.
Not really, because
not, no.
malloc tricks us a bit. But as soon as you use the memory, so let's say, okay, I reserve the memory and I write something inside. As soon as I use it, in this case with memset, and I just write 1 in every memory location, then it says after 32 gigabytes, now you have a memory error. And in this case, it stops because we are not checking here for null, and the program just stops. And maybe also you have a problem with the computer. So in this case, it does not work. But when we go back and you do not use the memory, the operating system says, you can have, 30,000, 80,000 gigabyte. As soon as you use it, then it's really assigned to you. That's very, very funny.
We've planned to show this today, but I think we'll show it.
I think we will show it next time. We have a short summary of today and what we talked about. So the memory layout, half of the memory is bound to the operating system. So we cannot access it. We have then the user space and we have the stack. And you will see this address quite often. Everything with 7 FFFFFF is most likely somewhere on the stack. We have the heap. This is the dynamic memory We have the data segment where we have all the constants and global variables. And we have a code segment where our source code of the program is stored.
And we are really just interested in the user space, not in the kernel space. So we should not access it. We're not allowed to access the kernel space. We're really just interested in the user space.
Yeah, we already talked about that. That's the same slide as before. And I also discussed that. One last slide, though, because it's very, very important. What do you think? Which segment is, or in which segment the variable my name is stored?
I'm really curious about the result of this question.
Yeah.
We know it's late, but still,
It's basically our real last slide. We have one more left.
Okay, let's wait a few more seconds, and then.
Okay, so we have a character pointer name, which is initialized with null, and then we call malloc and store an address there.
That is returned by malloc.
Oh, yeah. It's a very, very tricky question. The variable my name is a character pointer, and the variable is stored on the heap. Oh, on the stack, sorry.
On the stack,
The variable is stored on the stack, which is just pointing to somewhere on the heap.
But the variable itself is on the stack, not on the heap. We have seen it before in the slides. It's in the stack frame of, in this case, the main function. It's the variable my name. And this variable is pointing somewhere to the stack when we call malloc here in this function.
So this is very important to understand. It is on the stack. It just points to the heap. The array is then on the heap, but the variable my name is still on the stack of this function. Great. So I skip one on purpose because we have to finish. We will do it next time. And so as a short summary, what's the differences between the stack and the heap? The stack or the data of the stack is available until the end of the function. And the data on the heap is available until you free the memory.
So they have a different lifetime. And also the usage is a bit different between the stack and the heap. So we should use stack variables if we know the size of, let's say for an example, an array at compile time, but we should use the heap if we need it, or if we just know the size during runtime, or if we want to resize it, increase it, decrease it dynamically. So that's the big difference between the use case of heap and stack.
All right. Thank you very much for being here. That's already the last slide for today. See you in 2 weeks.
Yeah, see you in 2 weeks.